So from all the information we gave from our partnership with academia and industry, we started our lab work focusing on these two monsters we wanted to tame. The sulfonate azodides, which are recalcitrant and more difficult to degrade, hence leave a space for synthetic biology to act. Those were the two monsters we had to tame, and we focused on acid orange 7 and reactive black 5, on which we did our characterization assays. We started working with lignin peroxidase. This is an enzyme from a white rot fungus and has been shown to be very effective in degrading sulfonate azodides. We found the sequence in the registry, and we couldn't optimize it to E. coli, added a fabric prefix and suffix, and got the sequence synthesized from gene Oracle. Nevertheless, the transformations that they tried to do into E. coli failed, as the enzyme showed to be toxic to E. coli, and the gene showed several mutations and truncations. This kind of betrayed our project. It was toxic to E. coli, and we therefore moved on to, we pivoted to a different enzyme, which is called BSD-WebP. This comes from Bacillus subtilis, and it's defined as a didecolorizing peroxidase. It has a very similar range of substrate as lignin peroxidase, but as it comes from the bacterial kingdom, is more likely to be compatible with our host, E. coli. We therefore started the construction of this fabric from the Lisbon plasmid. We added a prefix and suffix, and we PCR amplified it, and we generated two different fabrics. One for our toxicity assays, which didn't have an inducible promoter, and another one with an inducible promoter, which could test the actual decolorization. As lignin peroxidase shows to be toxic to E. coli, I wanted to make sure that this other enzyme we were working with could have been possible to use in our host. We tested the toxicity, and therefore we drew our transformed BSD-WebP and compared to the control as compared to plasmid-free control, and this showed a very similar growth curve, which made us believe that this could have been a compatible enzyme for our bioremediation strategy. We hence started our DAD, the degradation and decolorization module, although we still prefer to call it diazodide. We grew overnight the bacteria to the highest concentration. We inoculated the dyes the day after, and followed by 24 hours, in which we controlled the stationary phase and the stage of decolorization, and the main decolorization module, which was in the last 30 hours, where we observed the main decolorization. So, go through quickly the experiment. After reaching an OD of about 1, we inoculated the dyes, and for the first 24 hours, we still didn't see decolorization, as most likely the azodides didn't enter the cell membrane. This was the same for acid orange 7, reactive black 5. After having left it for 24 hours in the shaking incubator, we left it for another 30 hours at room temperature, and then after another 30 hours, we finally saw the decolorization we were looking for. The decolorization occurred in the last 30-hour step, most likely because, first of all, the cells started to lyse, so it was much easier for the dyes to enter and came in contact with enzyme. And second, it was at room temperature, which is about the range of temperatures at which the enzyme is most active. We saw about 50% of decolorization for acid orange 7 and about 20% decolorization for reactive black 5. We therefore can say we started taming these two monsters and achieved the decolorization we were looking for. We also contacted and continued our work together with Lisbon to make sure that our data was comparable to what they did before in similar assays, but in enzyme-free conditions. I'll pass now the word to Joy, our biochemical engineer, who's been working on a scalable approach to this problem.
All right, so the whole point of this process was basically to have a cheap, quick, and efficient method to deal with this at an industrial scale. Here we have a process flow sheet, which actually constitutes the main components of our process. So firstly, the fermentation stage, where a sufficient amount of biomass was grown and later immobilized into the Saber unit, which is where the actual biocatalysis took place. We performed several mass balance calculations and fermenter design calculations in order to actually determine how we will implement this at an industrial scale. This is a schematic of how we envision it to look in a plant, and and the Sabre scaled ASO bioremediation module is highlighted over here. It basically is a plate and flame model, so it's very cheap to build, it's efficient to operate, and it actually dechlorizes the ASO feed streams sufficiently. Here we can see the main components, which is basically enough air in order to sustain the biomass that's immobilized on the plates, and the ASO breakdown products that would actually flow through. It's possible to invest further in downstream processing options based on potential lucrative products that would occur from the breakdown. We also use microfluidics to test the operation of Sabre at a very small scale, quickly and cheaply, through computer-aided design and rapid prototyping. We tested two main features. The first feature is the immobilization. So this is basically allowed us to figure out the flow rates and the residence times of ASO dyes in the module. And the second feature was the biodegradation, which we did by conducting small-scale experiments at a bioreactor, of a small bioreactor that we fabricated over there. So this was critical in figuring out the optimal conditions and optimizing the unit at a large scale to make it feasible and implementable. I will now pass the mic back to Georgia, who will tell you a bit more about modeling, which educated our lab.
So, the first kind of modelling that we did was essentially just to have a look at the pathways of products, which sounds really simple and you would expect it to be, but BSDYP, our main enzyme, is actually rather uncharacterized. So understanding the product pathways was a little bit difficult. So we started by creating an enzymatic time course for the breakdown of the ASO dyes as opposed to the creation of their products. And we did this for ASO reductase and BSDYP. And we used this enzymatic time course to do something called parameter inference, which uses Bayesian statistics to help us further understand the limiting factors, the bottlenecks, if you will, of the reaction, and hence inform our lab work to better solve these. So when we compared our predicted time course with the time course from data from the literature, we were allowed to understand the breadth of different parameter relative widths for each of the parameters, such as gene expression and efflux and intake of ASO dyes. So the more restricted the relative scale of the parameter, the harder that thing will be to create a successful ASO dye remediation chassis. And the things that we found were that intake of ASO dyes and efflux of ASO dyes and sulfonated ASO dyes would be the most difficult to deal with, which was mirrored in our lab work. The second type of modelling that we did was the chemical mechanism modelling. So as I mentioned before, BSDYP is not that well characterised in literature because it's fairly new. So there is very little understanding of how they actually work. So we worked with our chemistry department to further understand the chemical mechanism and to come up with one that might work. And we planned for experiments for radio labeling of oxygen and water to confirm this. So our modelling came side by side with our lab work, as did our policy and practice. And from the very beginning, we had a teammate called Kevin, who is a fabulous social scientist. And he started a sociological imaginings of the way our team interacted with iGEM and the way iGEM addresses issues such as environmental problems. So he used ethnography and did a discourse analysis to discuss the dual-use paradox. So essentially, the dual-use paradox describes the way we're using synthetic biology, which is a potential environmental problem in itself, to solve environmental problems. And this conforms well to the ecological modernization versus risk society theories. So to what extent are technological advances good, or are they just causing us more problems at the end of the line? And he really concluded that governance is the most important issue in this, and we really needed to tackle the trust erosion in the general public. So the way we kind of used his knowledge and his assessment of the way our team was working and the way our project fitted into general society was by having a panel discussion with the general industries. So our panel discussion was an extension of our wish to really interact with the industry. And we had already gone to ETAD, but we really wanted to go to a larger variety of industry members, such as ethical fashion, environmental and policy, and social and ethical sciences. And we had a really good turnout from all across the board. And the two things we learned mainly from this panel discussion was that firstly, current methods of biosafety weren't enough. People were still terrified. The second thing that we learned was that they didn't feel that it was just the scientists' responsibility to solve this problem. They believed that it was everybody's. So we wanted to work hard on a public engagement module that allowed the rest of the world to understand the problem so that we could solve it together. So we decided to start a campaign called Uncolour Me Curious, and we contacted a variety of artists such as Lyndon Gledhill, a bioartist from Philadelphia, Natsai Audrey, a bioartist from London, Central St Martin's Textiles Design Department, which is one of the foremost textiles design schools in the world, and the Slade School of Fine Art. And they produced artwork for us that we put in an exhibition in London, and we had a really good turnout, but that wasn't enough for us, because it only touched upon the people that lived in London or that could travel to London. So we decided that to have a greater reach, we would make a film. The Uncolour Me Curious short film, which was an abstract and conceptual art film that could really reach the rest of the world. And it did, because it was nominated for the Best Fiction Prize at the Biofiction Science and Art Film Festival in Vienna. And we went along, and it had a very good reception. And you can see by our Twitter analytics that around the time of the release of the film, we had around 2,000 impressions a day. So we really were reaching a lot of the world with this. The second thing I mentioned that we learned from the panel discussion was the difficulties of biosafety. So we decided to introduce a xenobiological module, which Eduardo will explain for you.
As we all know, biosafety is one of the critical issues when working with synthetic biology. And we believe that, yes, we can find biological solutions, but we can also work on xenobiological solutions outside biology to improve and never end our work towards the optimal biosafety. Our xenobiology, which aims to set new rules, new biological rules, and therefore has potential to be used as a new biosafety strategy. Our goal was to create an azeotrophic organism, therefore make our E. coli completely dependent on a xenocompound which is synthetic and it never been seen in nature before, and potentially this xenocompound could be derived from azodyes. The key feature of this azeotrophy is that not only the bacteria cannot biosynthesize the compound, but also it cannot find it in nature in any way because it's synthetic, it's man-made. We started doing this work using XenoRank. It's a software one of our team members developed and is available on GitHub for anybody to use, and ranks azodyes to the chemical similarity to essential cofactors. We therefore find a similarity between quinones, which are essential and needed by E. coli to survive, and the azodyes we are working with. The steps and the workflow of our azeotrophy was therefore, first of all, to knock out the quinone biosynthesis in E. coli. This can be done by knocking out ISPP, which is a gene responsible for the biosynthesis, designing compounds with relative similarity to quinones, so similar in their behavior to quinones, and chemical similarity to azodyes, so they could derive from the azodyes and be used for the azeotrophy. And the last step is doing directed evolution. As you can see, Charles Darwin on a Saturn V rocket is definitely a very fast form of evolution, and achieved therefore orthogonality from natural system with our xenocompound. It's been both a work, theoretical work, and we started working in the lab with a gene sciencing tool to pave the way for a new biosafety using a new form of biology. Georgia?
30 seconds.
So just to overview, by the end of the project, we had successfully degraded sulfonated azodyes in our remediation chassis. We had designed a scalable industrial bioprocess that could potentially be used in the future. We had identified limiting factors using modeling and improved chemical pathways in the literature. We did a sociological investigation and stakeholder engagement, and we designed a metabolic firewall for device safety using the new field of xenobiology. And we're very happy that you sat here and listened to us. Thank you so much for coming.